Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Shalom nama budaya. In this video, I will explain about metallurgy for the non-metallurgist, chapter 3. But the first, I want to introduce myself. My name is Putra Hutabarat, with student ID number 23055311075. I am from the Mechanical Engineering Study Program, Engineering Faculty, with Udayana University. Next, chapter 3, Mechanical Properties and Strengthening Mechanisms. The purpose of this chapter is to introduce the concept of mechanical properties and the various underlying metallurgical mechanisms that can be used to alter the strength of materials. Strengthening mechanisms are an important part of materials engineering and metallic materials offer a wide range of options in terms of mechanical strength and ductility. 3.1 Mechanical properties. When a force or combination of forces is applied to a material, the material responds with deformation or strain, often in a complex manner. For example, a load suspended from the end of a steel wire will cause the wire to stretch and the cross-sectional area to decrease, but the magnitude of the deformation cannot be observed without taking careful measurements of the length and diameter of the wire alone. Mechanical properties describe the relationship between the stress acting on a material and the deformation caused by the material as a result of the applied stress. The concept of stress in its most general form is the force or load divided by the area of the area acting. For a force F acting on an area A, the stress sigma is equal to F over A. Stress is often expressed in units of MPa equal to 106 N per square meter, or K is equal to 103 lbs per inch. There are two general methods used to characterize the stress: engineering stress and true stress. Engineering stress is most often used in engineering design calculations and is based on the original cross-section area A0 of the part or component under consideration. Because engineering stress is based on the original cross-sectional area, it does not take into consideration the fact that the cross-sectional area changes when a load is applied to the material. Next, in the conventional engineering tension test, an engineering stress-strain curve is constructed from the load elongation measurements made on a tensile test specimen, Figure 3.1. The engineering stress sigma used in the strain curve depicted in Figure 3.2 is the average or nominal longitudinal stress in the tensile specimen. It is obtained by dividing the load F by the original area of the cross section of the specimen A0. Sigma is equal to F over A0. Elasticity. Elasticity refers to the linear relationship between stress and strain in the elastic region of the stress-strain curve. When a crystal is stressed, its lattice strain is a response to the applied stress torque atom movement. If the bonds between atoms are not stretched too far, the crystal will return to its original shape after the load is removed. This is known as elastic deformation and follows Hooke's law. Modulus of elasticity is a physical property that describes the linear relationship between stress and strain in a material. Young's modulus, represented by E, is obtained under tension or compression loading. The elastic moduli of materials depend on their crystalline structure and interatomic bond strength. Materials with strong bonding have higher elastic moduli, while polymers have lower elastic moduli. The shear modulus G is the elastic constant under shear loading and is related to Young's modulus through Poisson ratio V. The compressibility of a material is determined by its bulk modulus K. Office yield strength, also known as proof stress in Great Britain, is determined by loading a specimen to its 0.2% office yield strength and then unloading it to a length that is 0.2% longer. It is commonly used for design purpose and avoids measuring elastic or proportional limits. Yield strength is important in estimating forces, performing operations, and designing structures to prevent accidents. Stress exceeding yield strength causes deformation, resulting in permanent deformation even after load removal. Initially, muscular tension more than compensates for the decrease in width, and engineering tension continues to increase. Then the decrease in area extends to increase in load due to muscular tension. Next, deformation before fracture measured material ductility and toughness. Brittle material is fractured suddenly with no plastic deformation, while ductile materials show significant plastic deformation before fracture. Ductile metals increase strain at a faster rate human plastic deformation. Next, graph 3.7 shows the engineering stress strain curve for various alloys. Engineering stress is nominal stress, not actual stress. At the beginning of the test, the cone of the thin specimen is evenly distributed along the test line and the nominal stress is almost the same as the actual stress. However, in the final part of the test, a cone occurred around the fault area, causing thinning. Next, the nominal stress strain curve figure 3.2 to 3.7 is also called the engineering stress strain curve to distinguish it from the true stress strain curve figure 3.8. The highest point beginning of the test, the cone of the thin specimen is evenly distributed along the test length and the nominal stress is almost the same as the actual stress. However, in the final part of the test, a cone occurred around the fault area, causing thinning. The nominal stress strain curve figure 3.2 to 3.7 is also called the engineering stress strain curve to distinguish it from the true stress strain curve figure 3.8. The highest point on the engineering stress strain curve is the test specimen ultimate tensile strength or simplified tensile strength. Next, some materials do not have a linear portion of their stress strain curve. For example, soft copper, gray cast iron, and many polymers exhibit this characteristic. The obvious method cannot be used for these materials. A common method is to define yield strength as the stress required to produce a given total strain. For example, E equals 0.005. Sometimes the slope of the stress strain curve is described by plotting triangular modulus or tangle modulus. Next, some metals like low carbon steel have a fluctuating yield point and yield strength at either yield point. The actual yield point elongation of low carbon steels occurs due to discontinuous deformation in which one or more discrete deformation paths, known as Luderlin lines, develop at different places in the tensile specimen. A similar phenomenon occurs in some superplastic polymers and metal alloys. In polymers, this phenomenon is called drawing. Creep deformation in metals happens at high temperatures, typical 0.3 to 0.5 times the melting point. High temperature weakens grain boundaries, lead to deformation. At low temperatures, deformation occurs within crystal structure under stress. Next, most creep testing is performed at high stresses and temperatures. The creep rate occurs in 3 stages: a rapid first stage, a stable second stage, and a third stage that increases until fracture. Next, the strength test results shown in various ways. Sometimes the results for a particular temperature are reported in the form of an isochronous stress curve, which is constructed from the same time point at the stress-strain relationship determined in the strength test figure 3.12. The elastic portion of the isochronous stress curve is added using the modulus values for the test temperatures determined in the dependence line. The stress then causes a curtain strain at the temperatures is then called the tensile strength of the material under that condition. Fatigue. Fatigue is the tendency of material to break under cyclic stresses. Fatigue fractures are caused by crack propagation and are usually brittle stress concentration points like surface roughness can determine fatigue strength reduction. Node sensitivity is measured by comparing fatigue strength reduction factor to stress concentration factor. Next, fatigue test results are generally reported in the form of a plot of stress versus number of cycles to cracking, called the S-N curve. Typically, the number of cycles is shown on a logarithmic scale and sometimes also stress. Most metals have a S-N curve that indicates longer life at lower stress. The fatigue stress of the material must be reported for a specific number of cycles, as well as the stress ratio for the test and the stress concentration factor in the specimen as holes. Next, toughness. Toughness is a material's ability to absorb impact without breaking. Node toughness is assessed through impact tests like the Carvey test. KLC measures resistance to crack propagation. Material strength is also related to ductility and hardness. Quality can be determined from tensile texture test. Hardness. The resistance of a material to plastic in the tension is important in selection and quality control. Next, 3.2 strengthening mechanisms. The basic structure of metal and alloys influences strength, softness, and toughness. The strength of the material can be increased in various ways. For example, by finer grains, trade-offs of softness and toughness may occur. Next, 3.2.1 Solid solution strengthening. Solid solution strengthening increases metal strength by adding specific alloying elements, causing strain in the crystal lattice. Dislocations are either attracted to or repelled by solid atoms, leading to increased strength. Next, the effect of several alloying elements on the yield strength of copper is shown in figure 3.16. Nickel and zinc are the size of copper. Beryllium and tin are different sized. The difference in atomic size and amount of alloying increases the strengthening of the solid solution. Next, solid solution strengthening of iron and steels. The addition of carbon to pure iron increases the room temperature yield strength of iron by more than 5 times. Picture 3.17. Next, 3.2.2 Effect and grain size. Grain boundaries effectively prevent dislocations because they cannot pass through high energy barriers. Grain boundaries block and stop dislocations in a lattice of individual grains. Grain boundaries also strengthen polycrystalline materials by restricting dislocation movement. Next, weakening of grain boundaries. Environmental factors can weaken grain boundaries. High temperature can affect grain boundaries to a greater extent than the arrangement of atoms within crystal grains. There is a temperature at which grain boundaries and granules have the same strength. Namely, they choose the cohesive equilibrium temperature. Below the temperature, grain boundaries are stronger than grain boundaries, whereas above it, grain boundaries are stronger than grain boundaries. The cohesive equilibrium temperature varies depending on the metal alloy, usually being about 0.4 to 0.5 times the melting point of the base metal on the Kelvin temperature scale. Next, 3.2.3 Cold working. If the metal is deformed at room temperature or less than 0.3 Tn, the microstructure becomes deformed due to cold working. Most of the engineered energy is distributed as heat, but about 10% is stored as energy in the form of gaps, dislocations, and stacking faults. Annealing. Heating and cooling a material to increase its strength. Annealing is the process of heating a metal to a certain temperature, holding it for a certain period of time, then cooling it gradually. The main purpose of annealing is to soften the metal before or during the fabrication process and reduce internal stresses in the material. This way, the metal can be worked further without causing damage. During annealing, 3 distinct processes can occur. Recovery, which relieves some of the stored internal strain energy by a rearrangement of dislocations into lower energy configurations without any change in the shape and orientation of grains. Recrystallizations, which is the replacement of the badly deformed cold worked grains by new strain-free grains. Grains growth, which occurs when some of the recrystallized grains grow at the expense of the other recrystallized grains. Next, recovery starts rapidly and decrease with time, while recrystallization slowly builds up to a peak right before leveling off. Recrystallization curves are typically sigmoidal, with an incubation period where no visible recrystallization occurs. During incubation, subgrain coils and grow until a stable nucleus for recrystallization from figure 3.21 and 3.22. Next, strain hardening parameters. Deformation during cold processing begins within the grain. Deformation triggers the movement of dislocation within grains that interact with grain boundaries. Next, an increase in the strength of metal when deformed indicates an improvement in work hardening. The end value is usually between 0.1 to 0.5 for cold working, where 0 indicates purely plastic metal without work hardening. Some metals such as copper and low carbon steel can increase hardness and strength through cold working, but reduce bending ability. Strain hardening of commercially pure aluminum. Cold working strengthening pure metals like 1060 aluminum, commonly used in corrosion resistant and easily set products such as sheet and plate. Temper O is soft fully annealed condition. H1 is a temper prefix for products strain hardened to desired strength without thermal treatment. H12 equals 2%, H14 equals 4%, and H16 equals 6%, and H18 equals 8% reduction. Next, 3.4 back to Dr. Wilm's mystery. In solution medicine, the goal is to develop and maintain an oversaturated solution of copper in an aluminum lattice. The results were obtained by rapid cooling to room temperature. When a sufficient amount of a substance is trapped in an oversaturated condition, enough substances are close together to form a settling zone. When this zone is small and continuous, the zone of deposition of trapped substance is called cohesive deposition. Cohesive depositional zones are small enough to incorporate the main lattice and thus cause strengthening by lattice distortion. Next, stage of precipitation hardening. Zone 1, formation of small particles, slight increase in hardness, and Zone 2, a maximum hardness, coherent precipitate with lattice, significant strength increase, and Zone 3, larger non-coherent precipitates, decreased hardness and increased ductility, averaging reduces hardness and strength. Next, portion of aluminium copper bias diagram showing temperature range for solution annealing and recrystallization annealing. Solution annealing at around 550 degrees Celsius helps reduce work hardening, while recrystallization annealing is done at lower temperature. Natural aging of alloy 20 or 17 duralumin. Wilms alloy contains 4% copper, 0.6% magnesium, 0.5% silicon, and other elements, with the rest being aluminium. It is used for various products and solution treating requires a specific temperature range. Examples of other precipitates age-hardening aluminum alloys. Age-hardening aluminum alloys are commonly referred to as the heat-treatable aluminum alloys. With few exceptions, most commercial heat-treatable aluminum alloys are based on ternary or quaternary alloys. 3.2.5 Other important strengthening mechanisms. Dispersion strengthening. Dispersion strengthening is a method used in alloys for intermediate and high temperature use. Similar to edge hardening, the difference lies in the thermal stability of the chosen particles. Unlike heat-treatable aluminum alloys, ODS aluminum alloy retains strength at high temperatures compared to pure aluminum and aluminum, magnesium, and Si system. Hardening due to the formation of martensite. Martensite is a non-equilibrium phase possessing a body-centered tetragonal or BCD crystal structure that forms during very rapid change in temperature. In general, martensitic transformations can occur in many types of metallic and non-metallic crystal minerals and compounds, just so long as the cooling or heating rate is sufficiently rapid. The basic mechanism of martensite formation involves the simultaneous rearrangement of many atoms, where a series of individual atoms move a distance less than 1 interatomic spacing. This small but orderly movement of many atoms changes the lattice structure of mere atoms into a BCD crystal structure. Okay, I think that's all I can explain. If there are any wrong words in the reading, I'm sorry. That's all, and thank you.